Okay, in this lecture, we're going to start in section 1.3. Let me share my screen. Hopefully you can see what I'm seeing. So this is a 1.3, and it's on algebraic expressions. So what is an algebraic expression? An algebraic expression is a combination of variables. So it's a combination of variables. And I'll explain what a variable is in a moment, although I'm sure most of us are, for the most part, familiar with what that is. I don't know why this is here. Oops. Sorry. So sorry. It's a combination of variables. And typically we use the symbols X, Y, and Z. Although it's not necessary that we do this, but these symbols are typically reserved to represent variables. It's a combination of variables using operations such as addition. Let me say that actually, using operations. Get rid of this right here. Operations such as addition, subtraction, multiplication, division, powers, and roots. So all or some or and all or some of these operations you can use, and you take combinations of these. So for example, we have the following are algebraic expressions. So this is an algebraic expression. This is also, and something like this is also an algebraic expression. So what it's typically bad practice to set up a definition without every term being explained, but that's okay. I'm going to explain what this means now, a variable. And as I said, most of us are probably familiar with what this is, but at this point in our mathematical education, we're supposed to be very precise. Mathematics demands precision and rigor. So a variable, let me say what a variable is. A variable is any symbol standing for or representing any I don't like the fact that I'm using any twice, so let's say a variable is a symbol standing for or representing any given number or element. So let's say this parentheses actually element from a given set. So a variable is a symbol standing for representing any given number or element or point or object in a given set. So you can't talk about variables without talking about sets, because set variables represent elements or numbers from a set. So a variable can really if if your set is not a set of numbers but something else, um for example, you can consider the set of all 2 by 2 matrices, and you can talk about variables representing a 2 by 2 matrix. So it's not necessary that a variable represents a number. It could represent just anything in that set. So the more general term would be maybe element or point in the set. Because as I said, you can have sets of 2 by 2 matrices. I mean, sets can literally consist of anything, but for us, sets are mostly going to consist of real numbers. Those are going to be the elements, real numbers. All right, so that's a variable. And so let's get back to, now that we explained what a variable is, let's get back to algebraic expression. So I'll set up this definition because this is a very important concept. One of the most important types of algebraic expressions are polynomials. We're going to see how important they are throughout this course. And then when you get into calculus, you're going to see that they're much more they're even more important than is indicated in this course. So in calculus, we're going to talk about what are called continuous. I know I haven't talked about what a function is, but we're going to talk about continuous functions. Um, and it turns out that every continuous function can, in a sense, be approximated by polynomials. And all that is made very precise when you take calculus, especially Calc 2. So polynomials are very important objects in mathematics. So what is that, though? A polynomial. So a polynomial um, in a variable x, and again x, you can have polynomials in more than one variable, but we're just going to look at a polynomial in one variable x. And again, x can represent anything. X could represent a matrix. So you could have a matrix polynomial. But again, we're just going to look at polynomials in a real number variable. So a polynomial in a variable x is an expression, so an algebraic expression of the form a n x to the n plus a n minus 1 x to the n minus 1. And then there's some intermediate terms, so we just omit them and use these ellipse marks to indicate that there are more terms here. And so you start this sum starts at a to the n x to the n, and it works all the way down to a1 x to the 1, but we're just going to omit the power 1. And then finally plus a0. So notice the powers of, so we have x raised to various powers, n minus 1, and then you work all the way down to the first power, and then finally, really, this is x to the 0, right? But we just omit that. So you work all the way down to the 0th power. But what exactly are these ANs and what exactly is n? Well, let's specify what they are. So where a0, a1, all the way up to an are real numbers. And these are called the coefficients. And n is a natural number. It's a positive integer, a non-negative number. Actually, I should say, yeah, let me not say it, because n could be 0, and the natural numbers, the way we define them, doesn't contain 0. So let's just say n is a non-negative number. Some people define, especially if you take a computer science course, Some people define the natural numbers to contain zero, and I think actually you should, and maybe I should have just went against what the book has said and just define. Um, yeah, let me just do that actually. So I know on the first day of class I defined the natural numbers to consist of 1, 2, 3, 4, but I'm going to redefine them because I think n the natural number should include zero. So n is a natural number, uh, and this is called. So what is we call this number n? The degree. So it's the degree of the polynomial. Um, and then these are the things in the sums. These right here are called the terms, and then we have we call an the leading coefficient. Let me um all right, let me not be confusing and just write it out the whole way. So we call an the leading coefficient, and a0 the constant term. All right, so let me just go over note. Let me just remind you also, note n is the set, and now I'm sort of redefining it, actually. I'm going to include zero, and then it's going to contain 1, 2, 3, all the way up to infinity. And as I said, or as I was starting to say, I don't know if I finished what I was saying, but this is common practice in computer science. So if you're a computer science major, you're going to take a computer science course, this is they tend to include zero in the set of natural numbers. So let me just go over this definition again. So a polynomial is in a variable x is an expression of the this form right here, and then the a0, a1, an are real numbers, and they're called the coefficients. So these are constants; they're fixed. They're a fixed, definite number. Xn, x itself is just represents any number, and then n is the as a natural number called the degree of the polynomial. Call an the leading coefficient and a0 the constant term. So we've already saw a polynomial actually. So this right here, this example right here is an example of a polynomial right here. So 2 is leading coefficient. 3 is a coefficient. 4 is a coefficient, but this is 2 is the leading coefficient, and 4 is the constant term. And this is a degree 2 polynomial. Oops. This is a degree 2 polynomial. Or second degree polynomial, or sometimes these are called quadratic. Let me just pull up the book so I don't have to write so much out. But here's a table with some examples. Um, yeah, so here's the example we already saw, this one right here. This is these names are not going to be they're not going to matter a whole lot. So don't even worry about whether something's a binomial or trinomial or these terms just to indicate how many these words just indicate how many terms are in the polynomial. So there's 3 terms in this polynomial, there's 2, and this one right here, 4. So now this is this is listing the terms, and then this is the degree. So this is a second degree polynomial. This one is an 8th degree because the highest power of x is 8. The highest power of x, and this one is 3, so it's 3rd degree. Highest power of x, and this is 1. Highest power of x is 5, so that's 5-degree polynomial. This one you can imagine, so it's just 6, but really it's 6 times x to the 0. So that means it's a 0-degree polynomial. All right. So because the variables represent numbers, they have let me actually just write this down. So because variables represent numbers, real numbers in particular for us, they have the same properties of numbers. And what does that mean exactly? Well, that just means that you can add variables, you can multiply variables. Variables have satisfy the associative, the distributive properties of numbers. In other words, variables inherit these properties. So that means if I have algebraic expressions, if I have two algebraic expressions, I can add them together, or I can multiply them together, or divide them. So we can do that. Let's just do that now with for an example. So this is example one. So this is adding. First of all, this is section is added subsection, I should say, is adding and subtracting polynomials. So adding and subtracting polynomials. So this is example one. So we're going to add two polynomials, and it's going to be pretty straightforward. It's going to be just like adding numbers in a sense. And that's because variables represent numbers. So this is part A. So we've got x cubed minus 6x squared plus 2x plus 4. So we have this one polynomial, and we'll just bracket it off. And then we want to add another polynomial. So this other polynomial is x cubed plus 5x squared minus 7x. So I'm going to include more steps than probably necessary, but I just want to illustrate all the properties that I'm using for variables now. So the first step is to just put powers of x together. Using these, now we're going to use commutative and associative property of numbers to put the x cubed with this x cubed, this x squared with this x squared, and so on. So and I'm going to bracket them off. So we have an x cubed from this first polynomial, and then x cubed for the second. And next we have this negative 6x squared in this first term, and then we have a 5x squared plus 5x squared. So right now I'm using the associative and I'm using the commutative property and then the associative property. And then now there's an x term here, but there's no x term in this second polynomial. So this 2x is alone. Oh, I'm sorry, no, I'm wrong. There's a 2x and then there's a 7x. So now we'll put those in parentheses like so. And then we have a 4, but this is the constant term, this 4. But there's no constant term in this polynomial. So this is the term that is alone. So now these x cubes right here, they have a coefficient of 1. It's omitted, but there's this coefficient of 1. So this x cubed can be written really as 1 times x cubed. All right. So with that in mind, I'm going to factor because x represents some number, so I can factor it. So there's a common factor of x cubed. So when you do that, those coefficients of 1 are left behind. And this is really the step that you probably in general don't have to do, especially on a test when you're pressed for time. But I just want to really illustrate what's going on under the hood, so to speak. So you have a negative 6x, or sorry, so again, this term right here, they have a common factor of x squared, so I'm going to factor that out, and that leaves behind the coefficients. And then again, I have a common factor of x here, so I'm going to factor that out, and then the 4 is just here. So now we can simplify this, and simplify this. So it's going to be 2x cubed. So So this is gonna be -1, so it's just gonna be negative x squared. And then this is gonna be -5, so it's -5x plus 4. All right. So I won't go over part B, that's not necessary, but there's a second part to the example. It's about subtracting. Um, yeah, it's about subtracting polynomials, and it's basically the same. Um, so now that's adding, subtracting, and we can also multiply algebraic expressions. So we looked at adding algebraic expressions, and we can also multiply algebraic expressions. All right, so let's just look at this example 2. This is a fairly straightforward example. So for example 2, I have this algebraic expression, it just happens to be a polynomial, and then I have this other algebraic expression, and I want to multiply them together, which I can do because x stands for some number. So the idea is to just use FOIL, just FOIL. So I'm gonna multiply the 2x, and I'm gonna distribute that through to the 3x and then the 5x. So I get 2x. Well, I guess I can just put that all together now. This is for this easy problem. So it's gonna be 6x squared, and then I have this 2x, and then the -5, so it's gonna be -10x. Now I'm going to take the 1, I'm going to distribute that through. So I distribute that through to the 3x and then the 5x. So I'm going to get plus 3x and then minus 5. And then I can simplify. Again, you could bracket these together and then factor out the x and then combine the coefficients. But at this point, having worked through this example right here, we know that to simplify this, we just simply add the coefficients. So this is going to be 7x and then 5. All right. I guess we can do this other example. It's just a slightly more difficult, but not much. So again, I'm going to multiply these two polynomials. And so now this is just two terms, but now this one has three terms, but it's not that much harder. It's still foiling. So I have this 2x, and then I distribute it through this polynomial. So I distribute it through this, and then this. So I get 2x times x squared, that's going to give me 2x cubed. 2x times the -5x, that's going to be -10x squared. And then the 2x times the 4, so it's going to give me 8x. Now this 3, I distribute that through, so it's going to be 3 times x squared, so it's going to be 3x squared. 3 times -5x, so it's going to be -15x. And then 3 times 4 to give me 12. And again, well, first of all, we're gonna have this 2x cubed, and that's because this is the only x cubed term here. But again, as I said, you could, if you need to, and then feel free to do this if you want. You could use the commutativity and associative property, put this x cubed with this x cubed, and then this x term with this x term, factor, and then simplify. But I'm just going to combine these steps together. I know that in order to combine this with this, I just simply add the coefficients. So this is going to give me -7x squared. And then I'm going to combine this 8x with this -15x. And to do that, again, I just simply add the coefficients. So it's 8 minus 15. So it's going to give me -7x. And then there's this plus 12 because this is the only constant term. All right, so it turns out that there's sort of a pattern maybe that you're seeing, and that's because there is something that you can generalize here. So here's some special formulas, special product formulas, and sometimes they're helpful and sometimes they're not. Sometimes it's just better to just work on the problem as an individual problem and not try to see it as fitting some pattern. Uh, so let me just pull up this table. So we have this table right here. Um, so this first one's probably maybe the most helpful one. The rest are not really that helpful. If you have something of this form or this form, it's usually just easier. It's usually, or even this one, this second one right here. It's usually easier to just FOIL, to 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 expand this and then FOIL. This one is really the only helpful one. It's the easiest one to remember. So this one is called the difference of two squares. So you have a squared and then b squared, and you can read this in one of two ways. First of all, it says that if you want to compute the left-hand side, if you want to FOIL of this, you just simply square the a, square the b, and take the difference. Alternatively, it says that if you say, oops, I don't know what's going on here. If you start with the right-hand side, you start with something of this form and you want to factor it, it factors in this way. So sort of two different ways of reading this. So let's look at an example. So let's see. It's example 4, and for part A, we have 3x plus 5 squared. And again, you can refer to the table and you can just write out what it equals without having to do any calculation, so to speak. But really, it's easier to just do the calculation. So I will do that out so you can expand it in this way. And then you just FOIL, and if you FOIL, I won't go through in as much detail as I did before. You're going to get 9x squared plus 15x plus 15x plus 25. And then you simplify that and you get 9x squared plus 30x plus 25. So part B, maybe this one will use the formula. So you have x squared, whoops, minus 2 cubed. So this is the cube formula. So let me write that down right below it. So we have our pattern. So we have x squared minus 2 cubed. So this is actually formula 5 on that table I showed you. So this one says that if you have something of this form, which we do, it's going to be a cubed minus 3a squared b plus 3ab squared minus b cubed. And so using this formula, this is a, this is b. You're going to say x squared cubed, and that's going to be minus 3 x squared times b, which is 2. And then it's plus 3, oops, a, so x squared, b squared, so it's going to be 2 squared, and then finally it's minus b cubed, so it's minus 2 cubed. And then, so let me just bring this arrow down, so then this will be equal to x to the 6th minus 3x to the 4th. Sorry, it's not quite, there's this 2 over here. So it's going to be 6x to the 4th. And then, so this 2 cubed right here goes 4 times the 3 gives you 12. So plus 12x squared. And then 2 cubed is 8, so minus 8. So yeah, so you can technically use this formula if you want to memorize it. Or you can just FOIL it, I guess. It's not that bad. So let me go through that also. So x cubed is the same thing as x sorry, x squared minus 2 cubed is the same thing as this. So I can write it like, there's three of these factors repeated. So now I'm just gonna FOIL on this, and then this one kind of goes along for the ride, and that's not a 3, that should be a 2, sorry. So this is 2. So now when you FOIL the underlying part, you get x to the fourth minus 2x squared minus 2x squared plus 4. And then that thing goes along the ride. And now you can just kind of distribute this whole thing through to this. So the x to the fourth times x squared gives you x to the sixth, and then x to the fourth, and then negative 2 gives you negative 2x to the fourth. And now we'll do this term right here. So now it's negative, when you distribute that through, you get negative 2x to the fourth, and then plus 4x squared. Now distribute this term. So you get negative 2x to the fourth plus 4x squared. And then I got to copy down on the next line because I'm running out of room. Now I distribute the 4. So you get plus 4x squared minus 8. So let's see, are we getting, so if we simplify this, so we get x to the sixth. So we have this x to the fourth, x to the fourth, x to the fourth. So when we combine all of those, we should get, so negative 2, negative 4, negative 6. So negative 6 x to the fourth, if I didn't. Okay, and that's good. So we got that up here. And then, so I did the fourth term. So now we have this x squared. So we get an x squared here, and then an x squared here. So that's going to be 4, 8 plus 12x to the 12x squared. That's good. We have that up there. And then we have this finally just the negative 8 right here. So a little bit longer. You could probably do it faster. I was trying to go through it slowly, but you could definitely do this foiling faster. And is it better to memorize this formula or to just do this foiling? I think it's just easier to do the foiling because this is just one formula you would have to memorize in order to deal with products. There's four there in total there are 5 of these formulas. So I guess it's just a matter of taste. Um I guess also I prefer this way because this when I'm grading your work, I can see all the steps and I can see if you do go wrong somewhere, I can see exactly where, and then I can determine, like how much extra credit I can give you if you happen to give a problem wrong. So I'll leave it to you to decide really which one you want to use. If you want to memorize a bunch of formulas, or just easier to just memorize one thing, namely how to foil, and the foiling is easy. All right, let's see what else we have. So let's do number, let's do example 5. So this is part A. This is again an example trying to illustrate how this special product formula works. So for A, this is actually this is the special product formula I would memorize. This one's the easiest one, and I would just memorize this one. This is not that bad. Again, you can always still FOIL it out. So remember, this is the difference of 2 squares because you have this term and then the terms repeated. And then the only difference is that this is a minus and this is a plus. So according to the difference of squares, you square this, and then you take the difference. So that one you can memorize, and it's really easy. And you get this. So you get that. And also this is B, let me do B. This is again using this, it's using that difference of two squares, that first formula. Let me just pull it up. Just to remind you, oops, what I used. I used this one right here, this first one. So this one I would memorize. This one is useful. This one comes up a lot. And that's the one I use, this first one right here. And I'm going to use it again. Although it's not going to at first be immediately obvious that I can use it. So what we have is we want to compute this product, and I claim that we can use that first formula that I wrote. So maybe it's not obvious at first because there's three terms. But if I use the associative property of numbers, it'll be clear exactly how I can do that. So now I want to put terms together. So I'm going to have parentheses inside parentheses. So I'm going to replace these parentheses with square brackets. Okay? Because I don't want to have too many, I don't want to have nested parentheses. You can get confusing. So I'm going to turn these parentheses right here into square brackets. And I'm going to associate an X and the Y and the X and the Y. Oops. And now here, now we can see that, yes, this is going to be the difference of two squares, right? So this is A, this is B. So it's A minus B, A, B, A plus B, right? We have the right form. And so again, according to that difference of two squares formula, I square the A. So I'm squaring X plus Y. And then I subtract 1 squared. And then this one, again, there's that special formula you can use, or you can just FOIL it. It's easier. It's easy to FOIL it. Do it on the side if you have to. So let's do this on the side. So you FOIL it, you get X squared plus XY plus another XY plus 1. And then you combine, you get X squared plus 2XY plus 1. So now we can FOIL this. And we get X squared plus 2XY plus Y squared plus 1, and then minus 1. Wait, no, this is not right. I knew something wasn't right. This is not plus 1 right here. That's plus Y squared. So X squared plus 2XY plus Y squared minus 1, and then that's it. You're done. All right. So the next thing, so we've been multiplying, and you can do multiplication sort of in reverse, and this is called factoring. And you're usually going to use those same formulas, or you're just going to be able to just guess and see exactly how. And if you're unsure how a given factorization works, you can just FOIL it, just undo it to see if you get the answer back. So we're going to look at factoring now. So let's just look at the difference of two squares formula. Let's write it quote unquote backwards. There's really no equations don't have an orientation. There's no direction, but we can in a sense assign direction. So I'm gonna quote unquote write the equation backwards or in reverse order. So if you read it, left to right, this is seen as this process is seen as factoring. So if you're reading it from left and right, you're seeing that you're viewing this you're viewing the left hand side and the right as the right hand side in factored form. And then if you read this from right to left, this is expanding. These two things are the same; they're literally identical. But sometimes this perspective can help you solve problems, certain problems. So if you read this thing from left to right, you're factoring. If you read it from right to left, you're expanding or foiling. So in this case, we want to factor, which is sort of the reverse of expanding or with a reverse of multiplying. So let's look at an example. So this is example 6. So we have A. So A is 3x squared minus 6x, and we want to factor this. So we can factor this pretty easily. So we just got to look at this is an algebraic expression. It has two terms, and so we just have to look at what's in common among each term. Well, so there's definitely an x in each one. In the first one, there's two x's. There's an x squared. There's x times x. And in this, there's a 3 here, but there's also a 3 here in disguise because 6 can be written as 2 times 3. So we can factor out a 3 first of all, and we can factor out an x. So when we do that, we get there's no longer a 3 here, and there's no longer an x, so we just have one x. And then over here, the x goes away, and we just have 2 because we factored out a 3 from the 6. And if you're unsure that this is correct, just or if you don't see why, just take this and FOIL it. Just do this in reverse. This right here is literally distributive. This is just the distributive law. So if I go backwards, I get the 3 times x minus the 3 x times 2, and then you can put the things together to get 3x squared minus 6x. So you really do get this back. So if you're unsure how a given factorization works, just FOIL or distribute. All right, so that's B. Or that was A. Let's look at B now. So we have 8x to the fourth y squared plus 6x cubed y cubed minus 2x y to the fourth. All right, so again we have this algebraic expression. This is actually a polynomial in two variables, x and y. And so we want to factor this. We have three terms in this polynomial, this algebraic expression. And so we want to look at what's common in each one. And just as we did in this part A, the best thing to do is look at the coefficients first. First, figure out if there's something in common with the coefficients. And there definitely is. There's a factor of 2. Each coefficient is divisible by 2. So there's definitely going to be a 2 in the front after you have factored. Now there's also definitely an x. Now figure out exactly what x to factor out. You need to look at the x to the smallest power. So we have x to the fourth, we have x to the third, that's smaller than x to the fourth, or here we have x to the first. So that will determine how many x's we can factor out from each thing. We can only factor out one, so there's going to be an x here. And the next thing to look at is there's definitely a y in common. So how much of y can we factor out? Well, we have to compare each term. So there's a y squared, y cubed. Well, y cubed is bigger than y squared. So far it looks like we can factor out a y squared. And then that's going to turn out to be what we can factor out, because this is a y to the fourth. That's larger. If this were just y, not y to the fourth, then we could only factor out y. So that's important that you compare all the terms. So we can factor out a y squared. So what happens when we do that? Well, so we factor out a 2 from the 8, so we get 4. We factor out an x from the x to the fourth, so we get x to the third. And we factor out a y squared from this y squared, so there's no y. What about the second term? Well, we factor out a 2 from the 6, so that leaves us with 3. We factor out x from the x squared, so that gives us, we factor out x from the x cubed. So that means we have an x squared left behind. And then we factor out a y squared from the y cubed, so that just leaves us with y. And finally, for the last term, we factor out 2 from the 2, so that just leaves us with 1. We factor in x from this x, so that leaves us with just x, no x, or just 1. And we factor out a y squared from the y to the fourth, so that just leaves us with y squared. And again, you can distribute this through to here, and you'll see that you do in fact get the right answer. And I need to pause this for a second, so I'll be right back. Okay, so the next thing we're gonna look at is factoring trinomials. Okay, let me just share my screen. All right, so factoring trinomials. Um, and the trinomials are just polynomials with three terms. General, we're actually going to look at a specific type of trinomial. What we want to do in this subsection is we want to factor trinomials of the form ax squared plus bx plus c, where a, b, and c, I actually put that word in there, where generally a, b, and c are integers. And remember, this integer it consists of all the natural numbers, so 0, 1, 2, 3, 4, 5, 6, etc., and all their negatives. So let's just look at some examples to see how this is done. So we want to factor, for example, x squared plus 7x plus 12. Let me write this better. So x squared plus 7x plus 12. So when you factor this, it's gonna the factors. So let's just put these parentheses to indicate that they're gonna be two factors, and the factors are gonna be polynomials that are with a smaller degree. So the degree of this polynomial is 2. So that means these are going to be first degree polynomials. So things of the form, say ax plus b, just the first power. So we can throw an x here, and then there has to be an x over here, because when we FOIL, we need to make sure that when we multiply the x's through, we get this x squared right here. So you can immediately just put those there. And in this case, because the leading coefficient is 1, it turns out that we don't want any coefficients here, okay? So then the next term is we have to have our constant term. We have to fill those in. And then there's going to be either plus or minus here, plus or minus here. So it depends on the signs, on these signs right here. In this case, everything's positive. So actually, in this case, these will be positive. But you do in general have to be careful what these signs are right here. If there's negatives, you might need to throw some negatives in somewhere. This part of factoring is more or less guess and check, and it takes getting used to. There's no simple way around there's no other simple way around factoring. You just got to just guess and check and just develop patterns and being able to see these patterns. So what do we know about these two blanks right here? Well, what we do know is that when you multiply them together, you need to get 12. So whatever numbers we put here, they have to be factors of 12. So really the best way to do it is just like list all the factorizations of 12. So there's 1 and 12, that's one factorization. There's 2 and 6 and 3 and 4, okay? There's also another requirement on these two boxes right here. So not only does the product have to be 12, so then in other words, they have to be factors of 12, but you know that when you FOIL and you cross multiply, you're gonna get those x terms and with coefficients, and those coefficients have to add up to 7. So there's two requirements here for these boxes. One, the product has to be 12. So in other words, they have to be factors of 12. And in this case, here are the factorizations. And then they have to sum to 7. And if you go through the possibilities, you can see that this doesn't work. Sum is 13. This doesn't work. The sum is 8. But this one does work. This because they summed 7. So you can put the 3 here and the 4 here. It doesn't matter in this case. And if you're unsure of whether or not this is the right factorization, just FOIL it and you'll see that it works. This gives you the right factorization. All right, let's look at another example. This is an example where the leading coefficient is not equal to 1. So this one is a little bit trickier, but it's not that bad. It's not that much harder. So what we want to do is we want to factor 6x squared plus 7x and then minus 5. So we'll put our parentheses like this. We need our x terms because when we FOIL, we need x squared, and the only way to get that is to have these x's here like that. Now, there's going to be a blank here, blank here, blank here, and then blank here. And then, of course, plus or minus, plus or minus. At the moment, it's not clear exactly, or maybe it's not clear. I'm assuming it's not clear to everyone whether it's going to be plus or minus. So we'll work on that in just a bit. So first of all, these blanks right here, we know again that you have to multiply them to get 5. So we need factors of 5. Well, there are only because 5 is prime, we only have this factorization. Now there's a lot of different possibilities. I should say actually we don't, it's not just 5, it's -5. So there are quite a few possibilities. It's 5 itself is prime, so there are only factors of 1 and 5, but we're looking at -5. So you have -1, 5. Those are possibilities for the blanks. You also have 1 and then -5, right? So and you can use these to fill these blanks right here. But what about these blanks right here, this one and this one? Well, you play the same game again, basically. So these two numbers, these two blanks right here, when you multiply them, they should give you 6, positive 6. So we need to look at factors of 6. We need them to multiply together to get 6. So there's 1 and 6, then there's 2 and 3. So we have basically 4 possibilities. Well, okay, so there's 2 pairs here and then there's 2 pairs here. So we have 4 possibilities to check. So we could do this pair and this pair, or we could do this pair and this pair, or we could do this pair and this pair, this pair and this pair. So you could do like 1 and 6, and then -1 and 5, or you could do 2 and 3, and then -1 and then +5. Lots of different combinations, but there's only finite limit. There's only 4 possibilities. So if you're unsure of which combination to use, just try all of them and then FOIL until you get the right factorization. So I'm gonna just in order to save some time, I'm gonna just show you the factorization that you need instead of going through all the possibilities. So it turns out that the right combination is 3 and 2. And then +5 and then -1. And you can see that if you FOIL this through, you get so what happens when you FOIL this through? You get 6x squared, then you get -3x, and then you get +10 x, and then you get -5. And you can see that you get this was the right choice. But if it wasn't immediately clear, just try all these possibilities, and it's annoying. I know it's annoying, but after you've done this a few times, you'll be able to see the pattern, and you'll be able to recognize the pattern, and it'll be almost immediately clear. You'll just be able to see it immediately, that the right choice of pairs. All All right, let's see. So what are we gonna work on next? All right, let's do example 9, part B. So for part B, we have we want to factor the following. So the trick here is to recognize, so we don't have x squared minus 2x minus 3. We have this 5a plus b. Um, but the trick here is to just replace this by x for a moment and to simplify the problem a bit. So this polynomial right here is of the following form, right? So let's just ask ourselves, can we factor this first? And if we can, then perhaps we can factor this one right here. So can we factor this one first? So let's write it over here like this. So again, we want to write it as a product to polynomials like this. And so in this case, we have the one coefficient, right? So we know that it's just going to be x here and then x. So this x with this x, and the coefficient is going to be 1. And so the figuring out what goes here is just a matter of looking at the factors of this. But there are only a limited number of factors. It could be like -1, 3, or 3, 1, -3. But we need the factorization such that when you sum them together, the two factors, you get this term right here. And this is going to be the right one right here, because when you do 1 minus 3, you get the -2. So the right factorization is going to be this minus so +1 minus 3. And again, if you FOIL this right here, you'll see that you get the left-hand side. So you get x squared. So x to here gives you x squared, then -3x, and then 1x. So that's where you get the -2x. And then 1 times -3 gives you this -3 right here. So this is the right factorization. All right. So um the trick then is just replace x by 5a plus 1. And when you do that, you're able to factor the original expression, the original algebraic expression. So this factors as follows. I'm going to write it on the second line. So this thing right here, according to this right here, this work right here, factors as follows. So it's going to be so we replace this x by 5a plus 1 and this x by 5a plus 1. So you get 5a plus 1, but then it's then it's plus 1, right? So it's 5a plus 1 plus 1 times 5a plus 1 minus the 3. So 5a plus 1 minus 3. So you get 5a plus 1, or sorry, 5a plus 2, and then 5a minus 2. And if you if you FOIL, you'll see that you get this back. So this is the correct factorization. So sometimes, sorry, it's good to, when you're given a problem, to look to see what's common. So we have this common factor of 5a, not common throughout the whole thing, because we don't have a 5a plus 3 here, it's just 3. But there is this 5a plus 1 that repeats. There's a square of it, and then there's the thing raised to the 1 power. So just get rid of it and just replace it by x. And then, so, reduce the problem to something simpler, in other words. All right, let's. All right. Let's see. All right, so there's a lot of examples, and I really realize we've done a ton of examples, so I'm going to skip over some, but I encourage you to uh, read through this section to go over the examples that we didn't go over. So now I want to go over factoring. Let's see. Let's see. Do I want to do? No. Okay. Yeah. So I want to do factoring with fractional exponents. So this one is a little bit different. The rules for this. So factoring with fractional exponents. So let's just jump right into an example. And I think this will be, let me check. This is the last one, I think. Oh no, there's one more example, but this is not that bad. All right, so this is example 14. So part A. In part A, we want to factor the expression, the following expression. So now we have x raised to fractional powers. So now x is a common term in a common factor in each of these terms, right? We just have this x to this fractional power. So we should be able to, in principle, factor out x to some power. But what power is that going to be? So the idea is, what you want to do is you want to factor out x raised to smallest power. And that's in general how this is always, it's still the same idea. Um, that you want to look at x raised to the smallest part, but it just kind of works out a little differently to figure out exactly how the factorization works. But again, first let's look at the coefficients before we factor the x. So there's definitely a factor of 3 in each coefficient. So we're going to factor out a 3. And we're definitely going to factor out x, but what's that power? Well, in this case, the smallest power is x to the negative 1/2. Okay. So we factor out the 3 from the first term. So what's going to be left is x to some power. Well, what's this power going to be? It's going to be, well, I need it to be such that when if I distribute this back through, I get 3/2. All right. So if you want, you can call it, let's say, like call the power n. So we want, there's going to be some more terms here, but I'm not worried about them. I'm just worried about this first term. So want m to be, and eventually you won't have to write all this down. You'll be able to just solve this equation in your head. So we want m to be such that when you distribute this through, you add these exponents, so when they should add up to 3/2, right? You should be able to get this 3/2 back. Well, you can figure out what that is pretty easily just by solving for m. So you're gonna add 1/2 to both sides, and that'll give you 4/2, which is the same thing as 2. All right. So let's put 2 in there. All right, now let's work out the next term. So we factor out a 3 from the 9, so you get 3. And now again, the power of this power, whatever that is, it's got to be such that if I distribute this back through and I add it to this mystery power right here, I need to get 1/2. Well, in that case, I think if you can set up a similar equation, you can call this m, and you want m minus 1/2 to be equal to 1/2. And if you solve for that, you'll see that it's going to be 1. And then the last term is going to be -6. So we factor out a 3 from that, so it'll be 2. And again, we're gonna have x to some power. But in this case, so what we want is that when you distribute this through, you get x to the 1/2. Well, the only way that can happen is if you have x to the 0, right? If you distribute this through and multiply it here, you add the -1/2 to the 0 and you get 1/2. So you want x to the 0, but x to the 0 is just 1, so don't write it. So let's since this is a somewhat complicated problem, let's actually check. Let's FOIL this through and see if we get what we started with. So we have 3x to the -1/2 times x squared minus 3x minus 2. All right, so I'm going to distribute that through, so I get 3x. So I have x to the -1/2 times x squared. So I add the exponents. So it's going to be x 1/2 plus 2. Now distribute this to the second term. You get -9, or sorry, yeah, you get -9 times x to the -1/2. Again, this is a 1, so it's plus 1. And then distribute to the last term, you get -6x to the 1/2. Now let's simplify those powers a bit. So just on the side, just to do this really quickly, 2 can be written as 4/2. So so 4/2 minus 1/2 gives you 3/2. The next one is a little bit easier. It's 1 minus 1/2, so it's going to be x to the positive 1/2. And the last term, there's not much you can do to it. And look at that, you get with what you started with. So the idea is, of course, as always, look at the coefficients, factor out what you can from the coefficients, and then these x terms, you want to factor out x, not just x, but x raised to the smallest power. And in this case, smallest power is -1/2. So that's why you have 3. That's why over here we have on the opposite side 3x to the -1/2. And then figure out what these powers are, and then x to the 0 is a matter of solving an equation like this right here. The idea is you want, when you distribute this back through this right here, you want the -1/2 and whatever power you decide to put here to add up to this power. And then again, when you distribute this through to this term, you want the -1/2 and whatever power you decide to put here, you want those to add up to this. So you're solving these like auxiliary equations, basically. You have these equations that you have to solve. And if I would encourage you to write out, if you're like me and you suck at arithmetic, and I definitely suck at arithmetic. It took me a while to get better at arithmetic. I would encourage you to write out these equations just for the first few times, because it can be a lot to figure out. It can be hard to determine what powers these should be. But that's how you do that. That's how you figure out what these powers need to be. All right. I think that's good for that. So the last one is factoring by grouping. So let's look at that. And then that's all we're going to do for today. So factoring by grouping. So in this case, we're going to have polynomials with 4 terms. And so it's not clear how to, it's not, we can't use really the same tricks that we did when we factor polynomials with 3 terms. That is those trinomials. But we can do this. We need a new technique basically to deal with these ones. So let's look at an example. So we have part A, example 15, part A. So this is polynomial we're given is 3x cubed plus x squared plus 4x plus 4. So the idea is if you associate the terms in the right way, then you can factor. So certainly all of these terms considered together, they don't have a term in common. Like these first three do, they have an x, and maybe you could factor out an x from this and try to do something from there, but that's not going to work out. So the idea is to split it in twos. So if you consider these two terms together, these definitely have a common factor. And if you consider these two terms together, they definitely have a common factor also. So let's do that. So we're going to put the x cubed and the x squared together, and then the 4x and the 4 together. So all together, all these terms considered together, they don't have anything in common. But if you break them into small enough pieces, they do have something in common. So from this one, we're going to factor out x to the smallest power, so that's x squared. That's going to give us x plus 1. And then over here, we're going to factor out, the only thing we have in common is the coefficient, so we're going to factor out the 4. So we get this. And now we've broken the problem down a little bit, and we've done one factoring, but we can also see that after this factoring, we have more common terms, x plus 1. So in this case, we're going to factor out this x plus 1. And if we factor out x plus 1 from this term, what's left behind is the x squared. And if we factor out x plus 1 from this term, what's left behind is the 4. And let's see. All right, so let's do part B, and then that's it. So part B is we have the following. We have x cubed minus 2x squared minus 9x plus 18. So again, all these terms considered together, they don't really have anything in common, but we can associate terms, and those associated terms will have something in common. So we're going to put the x cubed and the 2x squared together there, and the reason why we do that is because they have an x in common. And then we're going to put the negative 9x and the 18 together because they have a common factor of 9. All right, so now we're going to factor x squared from the first term. So we're going to get x minus 2. And then from this, I'm going to actually they have a 9 in common, as I said, this term and this term, but I'm going to factor out negative 9. And so that's going to become this. So now what we have is a common factor of x minus 2, so we can factor that out. Factor out an x minus 2 from this. What's left behind is the x squared. Factor out an x minus 2 from this. What's left behind is the 9. But we're not done here, actually, because this is a difference of 2 squares right here. Of 2 squares. Because 9 is the same thing as 3 squared. So we have x squared minus 3 squared. So we can factor that as x minus 3 times x plus 3. And if you're not sure that this is the correct factorization, just FOIL this. FOIL these 3 terms, and you definitely will get this back. All right, so just make sure you watch this video. I mean, obviously, if you're hearing this message, you did watch it, but make sure you're taking your notes, so that when we meet together on Monday, we can address any lingering questions.